So I'm going to try to get into this a little bit conceptually at first. Let me ask you a couple of key questions here. If I give you this graph, let's say it's like this. Now let me ask you one question to get us into it. This is related to what we were just talking about. Let's say this is the f function like this. Can anybody tell me what f of 3 is? 3. Now, if I ask you, what input do I need to get a -2 to come out? All right, cool. Are we all good with that? Now, let me make sure again. Is everybody cool with that?
Yes.
Okay, good. So this would be x equal -3, would lead me to that output. Now, I could very easily make another function that you can't answer this kind of question for. And that's what we're going to investigate, the difference between this kind of function and the kind of function I'm about to draw. And this should look familiar. So now, if I said, oh boy. So just to start us off, what's f of 1? 1. F of what? Now be careful about how I'm asking this. F of what number will give me 4?
2.
No. No. Has to be a single answer. I want one answer, and it has to be the complete right answer. Is there any way to do that? You can't work backwards here, can you? Can't be absolute value, because the absolute value actually gives you one answer. Can't be plus or minus, because there's no plus or minus scheme like calculator. It's going to give me one answer, right? There is no way to kind of work backwards. If I said the output was 4, so if I said, if I had somebody who started here, 4 feet up, and they were on this swing, they were on this tether, and they, whoa! It's like maybe a bungee, and that's why it kind of stretches out a little bit. You guys kind of with me here? Can you imagine this? I'm on this bungee, or on this thing, and I swing across. Whoa! Scrape my ass on the ground. And whoa! I said, at what time was I at 4 feet up? Can you tell me the answer? No, because there's more than one. I can't go backwards. I can't tell what the input would have been if I know what the output is. So if I know the output is 4, do I know what the input must have been? No. Why? Because there's more than one thing it could have been. You guys see, this fundamentally is different. For every point on here, is there more than one possibility? What gave me this? Only this. What gave me this? Only this. Cool? How are we doing so far? Okay, so somehow there's a specific word, there's like a subset of functions. They're the functions that can go both ways. One input gives me one output can work back to a single input. Let me say that again, because this is a key thing. One input gives me one output. That's because it's a function, but one output, I can work backwards to one input. This is funny because I've never said it like this. I've kind of skirted around the edges. This leads to the name of this type of function. It's called a one-to-one function. You get that from this, one-to-one. 1x gives you 1y, 1y works back to 1x, 1-to-1. So a function in general, for every x there's only one y. But for a one-to-one function, any specific x can only go with one specific y and vice versa. That is that they're paired together. They're not cheating on each other, right? That's another way to think of it. So this is a one-to-one function. Also just written one-to-one. Okay, cool. Now, what this means about this kind of function is I should be able to come up with a reverse function. If my output is now considered an input, so can't you ask me for like for -2, x would be 3. For 3, Not 3, Jeff. Negative 3. For 3, x would be negative 3. Jeff, come on. 3. So you can ask me for different outputs, what inputs would they have come from? I should be able to come up with a function to describe that. Well, how those inputs react. I can't do that here. There's more than one possible place it could have come from. So, if I have a function like, let's do this one step at a time here. You make one of these funky ones like I had on the test. Okay. Okay. All right. So is this one of these special kind of functions? And who can tell me what's the basic idea then? This wasn't one of these special kind of functions because there's a y that has more than one input that goes to it, right? So what kind of test? You got the vertical line test to see if you're a function, period. So it'd be a horizontal line test. It kind of makes sense. The vertical line test just makes sure that every x goes to one y. For a one-to-one, that has to work both ways. So I have to now do also a horizontal line test on top of that. This guy would fail the horizontal line test. There's at least one place where the y's are repeated, so two different inputs have the same output. Cool. Here, that doesn't have that problem, does it? Does it pass the horizontal line test? Definitely. No horizontal line goes through more than once. I love it. Which should mean I should be able to graph. So we're taking baby steps. I should be able to graph what the inverse function would look like, the opposite function. So this is f. We want to find the graph of this, and this is the inverse function. What that means is, if this function does to 3, like here, what does this function do? It takes negative 3 and it takes it to negative 2. The inverse function would take negative 2 and take it back to negative 3. So like you guys did. So for example, what value of x do I get a 1 output? 1. So f of 1 is 1. What value of x do I get a negative 2 output? Negative 3. Cool. So in terms of the inverse function, this would say f inverse of negative 2 is negative 3. It takes it back. So the original function does something to negative 3, makes it negative 2. The opposite function would undo it. Would take it from negative 2 back to negative 3. So let me give you, before we get into this graphing thing, let me ask you something that's a little bit easier. Okay, so let's say that's my function. What would be the opposite function? What's the inverse function? So for example, what is f of 7? 4. So I want the inverse function to take 4 back to 7. I want it to undo what this one did. So of course that function would be x plus 3. So that's really all I'm talking about here. Our functions are not going to be that easy. But that idea is always going to be that easy. It's got to be the function that undoes what the original function did. So in this case, f inverse will be x plus 3. You can see that happening there. 4 plus 3, 7. So visually, what does that do to every single point on my original function? What point is this? Negative 3, negative 2. So my inverse function is going to have to go through what point? Careful, no. The inverse function does not change the signs. It just takes the output back to the input. It undoes what was done in the first place. So what did f do to negative 3? It made it become negative 2. So what's f inverse going to do to negative 2? Take it back to negative 3. Why can we always find a way back? Because this function passed the horizontal line test. I can always find a way back. You with me? So far, semi with me? All right. Here we go. So let's kind of group this stuff together. Here's f inverse. F goes through the point negative 3, negative 2. So what's f inverse going to have to go through? Negative 2, negative 3. F goes through 0, negative 1. F inverse has to go through negative 1, 0. That's all there is to it. So on one hand, this is very crazy simple. Visually, you just take the points and you switch them because it has to take the output back to the input. They just switch. It goes through 1, 1, so that's not very interesting. This one's got to go through 1, 1. And F goes through 3, 2. So the F inverse has to go through 2, 3. So now F inverse is going to look like this. Negative 2, negative 3. Negative 1, 0. 1, 1. And 2, 3. Do you see any symmetry with how I've drawn, well, with how that came out? I've drawn it, I draw pretty bad, but at least you can still see the symmetry. Where would you say the mirror sits that would cause this reflection that we see? You guys with me what I'm saying here? There's definitely symmetry here.
1, 1 and 2, 2.
Yeah.
2, 2.
Right there. And we know what that equation of that dotted line is? Y equals x. Like you just said, 1, 1, 2, 2, 3, 3. What's the definition of that? Y equals x. So any function, if it has an inverse, the graph of the inverse will be reflected around the y equals x line. Why does that kind of make sense? What do we do with the points? Don't we reflect the x and the y? So all we see there is that's happening. It's going to reflect around the y equals x line. Yes, sir?
Is that 2.7?
This is 2.7. Cool. So we're trying to finish out chapter 2. Okay, so if I give you something like I did on the test, you know I'm going to. That's all you have to do is collect the points as they are now, flip them for the inverse, and then plot the points you got there. Not a big deal. Cool, cool, cool. All right. So what do you do when I don't give it to you visually? Calm down. You come up with a bumper sticker over there? You guys basically know what that looks like? Could you trace it out in the air for me? What would that look like if I graphed it, just the shape? No? Alright, good. So it kind of looks like that, right? I'm trying to draw it in your direction. Yeah. So it would look basically, and it's shifted over what direction, just as a review? Yeah. Back 3. So it looks like that. Does that pass the horizontal line test? Yes. So this should have an inverse.
Yes.
Yes, I like it. Now you can imagine the opposite function has to involve what operations? This one involves adding, so the opposite better involve, amazingly enough. This one involves cubing, the opposite better involve rooting. Cool. So the way you can always do it, because they're not all going to be this simple, you replace this with what it really is. What's f of x? What did it take the place of a long time ago? Y. And here's the really cool thing. This is where inverses are nice. You can see the concept in every problem you do. The concept is the input becomes the output and vice versa. You flip the points around, you do all this stuff. So in this equation, you flip the x and the y. That idea of the x and the y changing position, changing idea, it's doing the opposite thing to each other, that idea, you see that everywhere. When you go to solve this for y, what's going to happen? When you solve any equation, what do? You undo the operations that are there. So the end result should be the opposite function. So what's the first thing I do to solve for y? Cube root it. So you get y plus 3 is the cube root of x. And then minus 3. So officially, what symbol can I now write there?
Inverse.
I love it. F inverse. F of x is already this. We just discovered its opposite function, its inverse function. So let me ask you a couple of quick conceptual questions. If f of 7 is 5, f inverse of 5 is what?
7.
7, I love it. So don't make a big deal out of that. Right? That idea of domain range change, you play x and y is flipping. Right? F inverse of 5 is 7. What is f of f inverse of 2? I like that question.
Yeah, think about it.
2?
Why?
I don't know, it just sounds logical for some reason.
I like it.
The function of the inverse function is the answer. It's 2.
So what is f inverse? Whatever f inverse does to this, f is going to do the opposite to it, right? So if f inverse takes 2 and makes it 7, f is going to take that and make it back to 2. So these do cancel.
That's what I'm doing.
So it's just like cube root of x cubed is x. Because this is the f function, this is the f inverse function. They kill each other. I love it. So if you see that kind of thing, don't make too much out of it. It's a quick problem. Cool. Oops. Got it. So you guys try this. Find f inverse for these. Oh, let me make this. Calm down. I like the second one better.
So what x do we to both become y?
So remember the problem we had earlier, what was it? It was x plus 3 cubed, right? Remember I changed, what's the first thing I did? Switch the x and y. And the reason I do that little dotted line is because it really isn't an algebra step we're taking. It's a conceptual step. That's what we must do to find the inverse function. So we switch the x and y,
I get that, but.
and then we solve.
So we substitute both x's for y.
What's f of x known to be?
Butter.
Oh yeah, sure, of course. Yep. By the way, I will let us out a decent amount early, so don't clamor too much for a break. We will get out. I'm thinking about 2:30.
You want to go home and watch the game,
That's a good thing about being the teacher. No, there's more than that. Well, that's what so my dean doesn't watch my lectures outside. Jeff, I was good for YouTube.
Can you just like delete the part?
We're not gonna, yeah.
Didn't they go over this in class before this?
They did, but some people got here in a different route.
Oh.
They might not have done this in the, like, if they're fresh out of high school, they might not have covered this topic, believe it or not. Yeah. I was gonna poll you guys, how many of you guys have talked about logarithms before? Well, let me do it this way, how many have not? Be honest. Okay, a few of you guys. If you did talk about logarithms, you almost had to have talked about inverse functions.
Yeah.
Good, so this should be a review. But since we're out of that first chapter, I'm going to treat everything as I'm introducing it for the first time, because there could be a few people that it's true for. And I think we could all use a review. So the first thing I do, let me try to skip a step here. That'll be y, so I switch it with the other dude. Switch that to x and y. And then just resolve for y. Now, did you guys notice I first put a what power up here? I don't know if anyone was paying attention. I first put a squared up there, and of course, would that have an inverse function?
No.
Squared won't pass the... So I'd have to restrict the domain for that to work, so I'm not going to go there yet. So I want to stick with things that truly have inverses. The whole function itself has an inverse. So what do I do here? Multiply by 7, add 2, take the fifth root. So now you can call that f inverse. Cool. So some of you guys might realize this. There is a shortcut to this. I do still need to see the work, because, for example, this one you can't really get there too easily. But do you notice what's the last thing that this would do? For some input, the last thing it would do is?
5 root.
What's the last thing? If I put a number in here, what's the last thing that I would do? Divide by 7. What's the first thing this does? Multiply by 7. See, so not only have the operations reversed, but the order that they're done in have reversed also.
Could you do the last step again, please?
Oh yeah, so multiply by 7. So it's 7x. Add 2. So I get y5, right? And how do I kill a fifth power? Fifth root. Cool. How you guys doing? All right, all right. So what about this guy? Have you guys finished that one yet?
No.
All right, finish that one.
I gave up already.
All right, so you switch the x and the y.
You flip it.
So that's purely switching the x and the y, right? Now how do I solve this for y? What sucks about solving this for y? How many y's are there? There's 2 freaking y's.
Why?
So what I do, of course, what I definitely have to do no matter what is get this guy the hell out of the denominator. He's no good down there.
Yeah.
So I multiply by...
Okay, I got the right.
All right, now anytime you have more than one of the variable you're trying to solve for, let me blow your mind and tell you that you don't have more than one of them. I know, exactly. And that's all I'm going to say. See, no, if I subtract, get them all together. We know that from algebra. We know that we get everything on one side and all the stuff we don't want on the other side. So I'm trying to solve for y, so get all my y's on one side. So subtract that dude over. Now the reason I say there aren't really 2 y's is because what do I do now? Factor it out. So there's 1 y that was given to this x and this one. So I know when you see it, you're like, of course, but that's an easy one to forget. When you got more than one of the variable trying to solve for, what the hell do? You always do that. And what's the last step here? Get y by itself?
Divide by...
Sorry. Yes, so much. Oh my God.
Doesn't have
You
to
don't
do
know
that.
what happens.
It's just x to negative 1 x, and then you don't have to write y equals again, right? That's just in place of y, right?
Yeah, that's just to get the f inverse. I mean, you don't have to. Right here, I could just say f inverse equals this.
Yeah.
That's all you have to put. Yeah. Don't worry too much about the y. Yes, sir.
Split the fraction, right? Make it 1.
Yeah, yeah. From the beginning, you could. Yeah. You should end up
Yeah,
same place. Yeah. Cool. Here's something I want you guys to notice. In a little while later in this class, remember what I said this class was? Some kind of specific L? Yeah, graphing help.
Yeah.
What can x not be here?
0.
0. So the domain can't have, the x of 0 can't go anywhere. There can't be any points above or below x equals 0. Cool? That makes sense. That's undefined. But what if you take this and you turn that thing around, what output can I not get? See, it's easier to see here. Well, here you can still see it. 1. Because this is reversed, isn't it? So I can't get an output of 1. So I can't use an input of 0, and 1 somehow can't be an output. When we get to rational expressions and graphing rational functions, that will become very useful. Really nice, quick way to figure out what the range is. Okay, just keep that in mind. I'll bring that back when we get there. Oh, one last little thing in this section before we get too far away. How could I check this? So we just said on this problem especially, because it's kind of ugly looking. We got this, and we say f inverse is this. How could I check that?
X inverse is back to X.
I like this. That's better. Yeah, I could plug a specific number in, but that's not a proof of anything. How many specific examples would it take to prove this in general? Infinite number, every possible. All right, let's not do this. So let's plug this whole damn function in. What should the output be? If I plug into f inverse, I plug f of x. What do these two do? If it's true, these should cancel. I should be left with x. Let's try it out. So I'm going to put into, how did I do it? Either way, it doesn't matter. I'm going to put f into f inverse. So f was x plus 1 over x. And f inverse, hopefully, is 1 over x, what was it, minus 1? So to plug that sucker in there, this is where it gets neat. So I get, what is f inverse of that then? How do I write that?
1 over x plus 1 over...
Good, I like it. 1 over this, minus 1. Right, because I just plugged that in the place of there.
That and that.
All right, so simplify that.
It's Monday.
What my old teacher used to do is he'd say, EL, this is, when we ever saw this, we cringe, ELFS. And it's not somebody accidentally pluralizing ELF wrong. It's exercise left for the students. So whenever he'd write that out, we're like, oh shit, I don't know. But what do you do? I mean, what makes that problem really ugly? How many fractions are there? There's a fraction inside of a fraction. So let's kill one of them. How do I kill this fraction? Multiply by x. Now why am I allowed to do that? I can multiply that by x because I can balance if I multiply the top by x. So an equation, how do I balance an equation? I can kill fractions in an equation because I can multiply both sides by the LCD. If I have a fraction, I can multiply top and bottom by the LCD. That would balance it back out. You with me? I can multiply top and bottom of a fraction by any damn thing I want to except 0. All right. So you multiply an x through here, you'll get, on the top you get x. On the bottom you get x plus 1 minus x. So remember, what did we just do? I love it when I get to the end and everybody's like, okay. What was supposed to happen if these truly are inverses? They were supposed to kill each other and leave x. They did. They killed each other and left x. That's if they ask you, prove that these two functions that I give you are inverses of each other. This is what you do. Plug one into the other one. It really doesn't matter which one you plug into what. If it works one way, it's guaranteed to work the other way. It's kind of neat. Okay, so let me give you a little preview of chapter 3. Oh yeah, we actually do more than a preview. nice thing with chapter 3, and this is what I said in the email I sent out a little while back, that was sort of my don't completely freak out yet email, where I said a lot of what we talked about in the first chapter, that review chapter, is going to come back. We can do it and then get a little deeper with it. So you're going to see that kind of thing in this chapter all over the place. So one thing we did talk about back in the first chapter was quadratic and how to find the vertex, that kind of thing. Completing the square, that kind of thing. So before I get into this, let's do that. Let's focus on completing the square for a second. Somebody help me out here. If I had x squared plus 5x equals 2. Let's make it, sorry. Ah, screw it. Let's make it 5. Ah.
Half a 5 squared.
Good. So what number's going to go here? I can figure out in 2 steps. Yeah. First I take half of 5. And then I square. And I desperately want you to remember why that's true. It's just because if I did a few, I'd see the pattern. This number is always twice that number, and this is that one squared. So we're taking that into account. So if I just half that number, I see what this must have been. If I square it, I see what must go there. It's just using the pattern that we see in reverse. So that must go here. And here. I better do the same thing to both sides. And that's one of the easiest things to forget. We're like, well, that's got to go there because, well, you're adding it to that side of the equation. You better add it to the other side. Now, how does this help me? Because what's the next step? I have to factor this, and the nice thing is that pretty much factored it for me. It's x, and it's positive 5, so plus 5 halves squared. That's how this whole thing factors. That's nice. Because remember here, half of 6 is 3. That's what's in there. Half of 5 is 5 halves. That's what's in there. Squared is what's out there to make it work. Okay. And on this side I get 33. 4, so like. And then you can do what to both sides? And this is a nice review of how to handle squared equations. Square root. The minute you do that, you should plus or minus. It should be just second nature. It shouldn't feel right if you don't. It should be plus or minus. It's got to go there when you take a square root. You capture both roots, the positive and negative root. That kills that. And then I can do plus or minus 33 over. Well, square root of 4 is 2, so I can just make that 2 down there. So subtract the 5 halves and I'm done. How are we doing so far? Say again, sir? Square root of 4 is 2. So I took the square root of 4, but I didn't take the square root of 33 because I have no idea.
Oh.
So I just did the part I could and left the part I couldn't. Cool. Now, I'm hoping some of you guys are like, okay, Jeff, that's nice, but why the hell would I do that? Because what would you do from the first step there if I didn't say you had to do completing the square? What would you do here? What should you do here? Minus 2 to get equal to 0 and then factor. In this case, it won't factor. So what do you use? Which is what? All this crap, blah, 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 blah. And of course, if you do that right now, you're going to get this. You can kind of see it, negative 5 plus or minus root 33 over 2. You can see it? Because what's b? 5, so you get negative 5 plus or minus. 25 minus 4 times negative 2, so plus 8. 25 plus 8 is 33. Twice 1 is a. Right? Wow. Dude. It's not David Blaine-ish, but it's still Here gets closer to David Blainish, just to make his name into an adjective. Everybody know David Blaine? Is he still somebody that people know? Magician, yeah. I love the parody. Have you ever seen the parodies? Yeah. David Blaine.
Oh, yeah.
Anyway, sorry. Inside joke. What? All right. Before I jump into this, we're going to complete the square on this because we're crazy. Well, I want to first show you what the hell do you do when you have like 2x squared plus 12x, and you want to complete the square here.
Two like terms and then divide by 2.
Yeah, take a 2 out. So say it's equal to 1. Just to make this an equation. You with me? So I haven't done too much yet. Why do you take a 2 out? Because in order for a completed square to work, it needs a 1 there. But here's where things get a little freaky. What number has to go here?
3 over 2 squared.
6 over 2 is 3. 3 squared is 9. What did you actually, now I know I just put a plus 9 right there, but what actually happened to this side? 18, so you better add 18 over there. Right? Because what just happened here? What is this side? It's 2x squared plus 12x plus 18. So I better put a plus 18 there. You with me?
Yes.
The ones we've been doing so far are easy because they had a 1 there already. So 1 times whatever is that thing. I didn't have to worry about it. So here, if I take an A out, oh shit. What happens if I take an A out? What do I get here?
B over
I like it. Good. And then I leave a little space. And I took my minus C over. Is everybody kind of with me here? I don't care that there's an A, B, C. You just start attacking. That's the beautiful thing about completing the square. It's just the same process every time. You move this guy out of the way. Take whatever the hell that is out. What's the next step?
You have to square.
So what's half of B over A? 1/2 of B over A is B over 2A. Starting to look familiar. I like that. Yeah.
Square.
So B squared over 4A squared?
Yes.
So you don't worry that these are not numbers. I don't care. You do the same thing every time. So where's this go?
Both places, inside and outside.
Yeah, so it's got to go plus B squared over 4A squared. Right?
Then minus.
And what did I actually just do? Plus B squared over 4A, because I did A times this. Won't one of the A's cancel? Just like with the 18, is 2 times 9 is 18. A times B squared over 4A squared is B squared over 4A. I'm not going to make you do this by yourself. If you want to, you can just stop right and just kind of stare blankly ahead. Okay? Some of you guys must have seen this before, I'm sure. Depending on your teacher. Of course, I just erased the thing that was going to help us. B over 2A, that was the first step, right? So this tells me what? This tells me what has to go here. This tells me what? How this is going to factor, right? Thank God. That looks disgusting. So it already told me how it's going to factor. It's going to factor like that. Yes, sir.
What if you do times like A first, then I get the other side?
I did. So this times this,
Yeah.
one of the A's would cancel, so that's why there's only one A down there. Cool. Oh, square, yeah, thing. So far, so good. So I got A times x plus b over 2a squared. Put this together for me. Won't you have to multiply this by 4a, so it'll be b squared minus 4ac over 4a.
Isn't it 4a squared?
Not quite yet. We haven't divided that down yet. Are you guys semi with me a little bit, tiny bit? I mean, I really desperately want you to understand. You look up at what we're doing, and it's real easy to go, what the? But every step by itself, you always cut this in half and square it to figure out what goes here. The first step tells you how it's going to factor. It's like it's doing it for you. Part of it. Before I square root, what should I do?
Divide.
Yeah, divide by that a, so it's really just going to... You ever seen that? Division by a is multiplication by 1 over a. It makes it easier when you have fractions there already.
Yeah.
Okay, there you go. So what do I get over here? 4a squared. Now I square root. When I square root, I better plus or minus. So now I get x plus b over 2a equals plus or minus square root b squared minus 4ac. What's the square root of 4a squared? 2a. And then subtract this bad boy over negative b over 2a. And then I can put it all over 1 because they have the same denominator, right? That's the quadratic. That's where it comes from. So just to take you back a second, did we solve this problem by completing the square? Didn't it take a long ass time?
Yeah.
Compared to this would, right? Because this is completing the square solved. So instead of plugging numbers in and then completing the square, they completed the square for every possible a, b, and c, and that's what this is. So that's why this is quicker, because it's already got some of the work done. Maybe.
Yeah, we're there.
We're there? Yeah.
Not only am I with you, I wish that my high school math teacher pointed it out like that, instead of just, you need to memorize the quadratic equation.
I mean, it's nice to see where these things come from, and it's nice to see why.
My hands are...
I mean, now, at this point, I wouldn't blame you and said, well, why is completing the square even still around? Well, because I have to be able to put circles in the standard form so I can see the centers. You know, completed square has uses where you want to try to get things into one thing squared. And we see that in circles, hyperbolas, ellipses, all those kind of things that we're going to be doing later. So that's why completed square still is needed. But when I have a problem with this, if I don't say use completed square, dear God, don't. Right? It would work, but this is a shortcut to completed square. Okay. Whew. Oh, so one last little thing. I did talk about this. Remember what I said about this? Yeah. So everybody got what they want here? They actually have this whole thing in the book too, I think.
That's the first.
Yeah, page 227, they have this. So this is the last thing we'll do. Let me explain a little bit about the b over 2a. We'll do a specific problem that illustrates that. Then we'll all go somewhere else.
Happy.
You don't have to go home, but wherever you want to go. Yeah, this piece is the discriminant. So remind me, we did this once before. If this is -1 and this is 7, can anybody tell me where that vertex is? What's the x piece? 3. It's got to be 3 because it's right in the middle of those, right? So how does this expression, let me break that up a little bit so it looks more like what we had here, relate to what I just said? How does that relate to this picture at all? Possibly. I mean, when you solve this, when you use this, what kind of problem did it come from? X squared plus bx plus c equals 0. So what would you find then? This finds the x-intercepts. This is the x-intercepts that you're finding. So that's why you can't use this when I'm asking you to factor something. You could actually, but you have to be really clever about it. So some of you guys try to factor using this. Not going to work because it's not an equation. So this would represent the x-intercepts. One x-intercept would be negative b over 2a plus this business. And the other one would be positive b over 2a not positive, yeah, minus and plus. There you go, Jeff. Eventually. That makes more sense. So the negative one and the positive one. Okay. So what's right in the middle? Minus b over 2a. So specifically, this is easy because I can see that this would have come from like this here, right? So if I have this function, what's the vertex? Right in between -1 and 7? It's at 3. And then how do you find the y piece of the vertex? Throw a 3 in there. You get 4 times -4, -16. Bam! But now I'm showing you, and even better, what if they give you something you can't factor, the bastards, right? Then you do this. Negative b over 2a is right in the middle of negative b over 2a minus this, negative b over 2a plus the same thing. It's got to be right in the middle, of course. Right? So here's a specific concrete example for everybody tired of ABC. Find the vertex. It's going to be a two-step problem. Find the x piece of the vertex. Find the y piece of the vertex. Right? The minute you know x, you plug in to figure out y. Not a bad problem. Right? So one, how do you find the x piece? Yeah, x equals negative b over 2a. What's b? Negative 12. What's a?
6.
3, but you're thinking ahead. I like it. So 12 divided by 6.
-2.
Positive 2.
Oh, 2.
So there's the x piece. How do I get the y piece? Plug it in. 3 times 2 squared minus 12 times 2 plus 2. Negative 10. Cool, man. So what's the vertex? 2, -10. I love it. It's got to be a point. So I got the x piece, the y piece. There it is. Kick ass. So if they have you a problem and they say, what's the maximum profit I could expect? They give you a function, negative b over 2a, plug it in. There's your maximum profit you can expect. Of course, it's got to be, hopefully it's an upward parabola. Right? If it's a downward parabola, there's two things. I mean, downward parabola. If it's an upward parabola, that means your profit could theoretically go forever up. That'd be neat. So probably most profit functions are somehow limited in their profit-making capability. Right? And it's just a joke for me. It's all right. Just for you, Jeff. All right. So that's plenty. That's just part of section 3.1. So next time we'll try to get further into chapter 3. Again, as always, don't get used to leaving this early. As always.
I have a class at 7. It says teacher.
So what is this, Ryan? You just plug it in, right?
Oh yeah. So negative over 2, got 2. To get the y from the x, you just plug it into the function, right?
If you have all this,
That's the function there, right?
Yeah.
So if I know the y-intercept is at x equals 2, I mean the vertex is at x equals 2, how do I get the y piece?
No, how do we map?
What about it? Oh, I'm sorry.
Yeah, that's good. I was going to write it down.
3 times 2 squared minus 12 times 2. I'm
Oh,
just making x
right.
2, yeah.
That was like 21. I was like,
I got you.
yeah, that's sorry.
Yeah.